Today we've got the honor to have Matthias Bethge visiting us, continuing the successful series of deep learning seminars so far. So Matthias Bethge is a professor of computational neuroscience at the University of Tübingen and director of the Bernstein Center Tübingen. His research lies at the interface between artificial intelligence and neuroscience, and focuses on uncovering the representations, algorithms, and neurocomputational design principles for perceiving neural networks both in brains and machines. A practical example of the outcome of his research has been a new method for creating artistic images, and the website, you can see it up there, deepart.io. So he's like one of the authors of the paper that everybody probably has seen with nice pictures. You put your own picture and you make it look like Van Gogh or whatever else. Some examples here. So today he's going to talk about modeling human vision with deep neural networks. And well, the floor is yours.
Thank you so much. Actually, if you have done something like this with deep art or neural style transfer, then when you give a research talk, you wonder how can you make your talks as entertaining as this stuff, and it's of course a hard challenge. And today I will rather talk about more my scientific motivations and not so much about this. So I was supposed to put this online. Of course, I'm happy if you want to try it out, and I do it from time to time myself, that I try to create nice images, but the actual drive of my research is more that it's actually that I want to understand the brain and functions of the brain, and that has also some relation to computer vision. And sometimes I feel a bit torn between these two fields. And so I'm going to neuroscience conferences where I don't need people from computer vision, and then I go to machine learning conferences where I don't need people from computer science, from neuroscience. And I try to explain a little bit why I'm trying to be in these two fields. Just need to figure out now where my presentation is. Just a second. It worked. Okay. Right, so I will talk about modeling human vision with deep neural networks, and in the beginning I thought this would be up while you were giving the introduction, so to have some fireplace here to make it cozy for everyone, but it's actually an advertisement of a paper that I won't talk about, where we extended the texture synthesis that also underlies this deep art algorithm, basically that extracts the texture of a paper, of a painting to be imposed on another one, where we extend it to the temporal domain. So you can also do parametric texture synthesis with deep neural networks by doing that on consecutive frames, and then you can, in an autoregressive fashion, generate dynamic pictures. And so I would have more examples, but it's just a teaser. So the goal for understanding the brain for me comes really from an evolutionary perspective. And when I think about what it means to understand the brain, I really think about understanding the neural basis of the animal's fitness. And of course, we don't know what the global objective function is of life, right? So it's we all know these trade-offs all the time. But we can look at individual skills that are definitely important to contribute to the animal's fitness. And these individual skills can be defined and tested via benchmark tasks. And so my approach to understanding the brain really is to understand how the brain achieves high performance on relevant benchmark tasks, like, for instance, object recognition, or to make it more, to illustrate it a little bit. Imagine your face recognition wouldn't work so well, such that you would confuse the face of your partner all the time, that might lead to confusions that could affect your biological fitness. Right? And, so there, or if you don't know how to recognize objects fast enough when you're sitting in the car, that would also could have some fatal consequences. So from that point of view, there's a tight connection between computer vision and neuroscience, because computer vision seeks to understand how computers can achieve high performance on ecologically relevant visual benchmark tasks. And so in most neural models in neuroscience didn't, have the ability to account for actually solving those problems, and so we need to bring those together. So as you might have figured already, so I focus in my research a lot on vision. So I'm also sometimes consider myself rather a vision scientist, and with the idea that also maybe there's a possibility to understand vision, whatever it is. And the way how I see that is that vision has to do with an efficient, approximate, inverse 3D graphics problem. So we have a relatively clear sense of how images are generated in physics. So we have source of light, we think of the world as a three-dimensional world, where this light is scattered at the surfaces, at the environment, and then it's collected by some sort of camera generating an image here. And in order to vision, we have to decompose the variability that is generated in these images into causal factors such as changes that are due to different illuminations, changes that are due to different poses at which the object may be posed, or the different angle with which we focus the camera. Background clutter may change from instance to instance, occlusion may be there, and so on. So there are different factors which make it hard to identify any of these causal factors individually. So it's a complicated inference problem. I will exemplify this a little more with an example of illumination and object surface. So if you think of the forward direction, these two things are combined in a sort of multiplicative fashion. And so in the end, you have only one image that doesn't tell you how these things have been combined, and then the vision problem is really to disentangle these two factors and ideally to be able to say what is the structure of the object surface and what has been the illumination. And as an illustration how dramatic this variability can be, I show you this example here of three scenes that are identical and just the illumination changes. And here's at this location, so always the same location, I show you the pixel intensity variations. As you can see, they are very, very different. So you can have really huge differences in your sensor signals and the pixel intensities, yet our perceptual interpretation is the same. And so it's a challenging problem, and that's why vision is really a very special property in the universe, right? So actually, this here is the only place that we know of that vision systems exist. And one reason why they exist is because brains exist there, so that's where we locate the Earth. And so it's quite intriguing that we have a system. So if there wasn't a system that we know that can do this inverse problem, then we might not even think about it, right? So the brain is like an encouraging example to hunt for this ability. and amounts to the bigger question. So vision is just one example. How does the brain model the world? And, of course, the world is always much larger than you have neurons in the brain, and so it's also a lot about finding efficient representations and efficient approximations. So we won't be able to do like a perfect inversion, but we have to find the right approximations. And as I mentioned earlier, so these two fields, artificial intelligence and neuroscience, basically separated for a long time, or most of the time they don't talk so much to each other. In that sense, I feel that the time of deep learning really is a golden time that brings these two fields together again, in the sense that we can actually now relate neural mechanisms that we observe in the brain to our artificial neural networks. It's relatively easy to discuss whether an artificial neural network resembles networks in the brain or whether there are discrepancies. And at the same time, these are the most successful algorithms for solving these ecologically relevant problems at the moment. And so it really builds a bridge that is very interesting. And also the roots, of course, for neural networks come from neuroscience, so I thought I'd give a very quick intro to that. So I think this is an important date where Qualcomm and Pitts came up with a very, like the simplest abstraction you can think of a neuron as a threshold unit which integrates linearly over its inputs and then does nothing but this one nonlinearity, the thresholding. And the idea that by combining these little computational functions, you can generate something complex, right? So if you have simple, it's similar to Boolean networks also. If you have an XOR computation or other simple, but they have to be nonlinear. So you need one nonlinearity, and if you combine one nonlinear element, then you can do basically universal computations if you have enough of those units. So in the deep networks, specifically, also specifically those that we are using in vision, in computer vision now, there's an important precursor and inspiration by Fukushima in 1980, which was inspired by findings of Hube and Wiese about simple and complex cells, how they, again, was very brave in abstracting away from the neuroscience and thought, oh, maybe that's how it works. You just stake these processes, and this may be the operation in the ventral stream in the brain. And so this was basically just an abstract model of how one could have thought about this processing in the brain, but it didn't work, right? So you couldn't do object recognition or anything with it. It just resembled certain properties of structures that you find in the brain. And for the neuroscientists, basically, this was way too abstract, right? So, I mean, it's a very coarse model nowadays. And before, like 10 years ago, it was also not useful in terms of computer vision, right? But then, in 2012, someone, Alex Krichevsky, used this type of architecture. So the network by itself, if you look at it through the goggles as a neuroscientist, you might not even be able to tell the difference because the difference is hidden in the synaptic weights. And the problem was by handcrafting these synaptic weights, you wouldn't get this network to perform well, right? And only due to faster machines, better optimization, and lots of training data, we now found a way how we can adjust the synaptic weights of these networks that the network is doing better than other algorithms that people have tried before in computer vision. So when that big success happened, I still wasn't convinced that this is too interesting for me. So the task where this success of AlexNet was demonstrated was in the ImageNet benchmark, which is a task where you have lots of images downloaded from the internet, basically, so photographic images, and you have to classify them into 1,000 different categories. And you may think about what's special about this task. Apart from that, I wouldn't be able to tell apart so many different types of cats or so many different types of dogs and other animals that I'm, especially in English, I don't know the names of them. But also, also in German, I couldn't tell many of these apart, right? And also, if you compare it like to MNIST, the handwritten digit recognition task that has been used for decades in machine learning, it doesn't look so different, right? I mean, of course, it's not photographic images, but instead of 10 classes, we have now 1,000 classes, and instead of black and white handwritten digits, we have photographic images, but it just doesn't seem like a super qualitative difference, it just seems to be larger, bigger somehow. Scaling up, bigger computers, more categories to be classified. But the general experience of learning in computer vision was if you train on one data set, it doesn't generalize to new tasks and new data sets. And one thing that is really important to me as a feature of explaining the biological fitness of the that we achieve with the brain is that we have one neural network that can answer all kinds of questions. Object detection, depth estimation, material inference. Yeah, one can try to break it down in many things. You can also say car driving or searching your keys in the room. Or actually, I find it always quite amazing when I fly. And you look from a quite big distance on the Earth, if you have clouds, that your visual system still works. Yeah, even though you are not in your usual setting, you're much more far apart, and you can recognize individual objects, and so it's quite amazing how general our visual system works. And so the question, one important question is whether we are able to build a network that somehow can cope with a variety of vision tasks, with a variety of questions that the visual system should be able to answer. And what convinced me then to be super interested in these networks was a paper from Trevor Derrick's group from Berkeley, which came out already on arXiv in 2013, and which was basically showing the success of transfer learning with these networks. So what they did is they took AlexNet and they retrained AlexNet with relatively little data on all kinds of other benchmark tasks. And then showed that they achieve better than previous state-of-the-art performance by using this network with little retraining on these new or on these other data sets. So the main idea of transfer learning is that you have one data set here where you have massive amount of data. So for ImageNet, there's 1 million training images. And so which is for many other tasks, you have to work with 10,000 images only or so. And it turns out if you first train your network on this task and then you use the data that you have for your other tasks, say for depth estimation, then you perform much better than if you would try to train your network from scratch on this task. So the knowledge, there's some general knowledge about the visual world in this object recognition task that generalizes to many other problems. And that, yeah, given that I think that this generality is a very important thing, I got quite excited. Basically, my lab started to work on deep learning the next day, and so since then it became more and more important. And the first thing that we did is transfer learning, trying out transfer learning ourselves, whether that really works and whether it works for us if we do it. And at that time, we were working on the so-called bottom-up saliency problem, which I can explain here. So it's related to the MIT 300 saliency benchmark, which contains a little more than 1,000 images, for which they have recorded the fixations where people look in these images. So basically, human subjects will sit in front of the screen, and they had the task to look around in the images, basically. It's the so-called free viewing conditions, no special task, just don't fall asleep, look at the images, and then you record these point densities generated by your fixations. And that's like several subjects per image. So there are about 150 fixations per image or so. And from that you can estimate two-dimensional probability densities where given this image people are likely to look at, or given this image where people are likely to look at, and you can see there's a difference, so there's information in the image that determines where you look. There's also some general structure, so if you average over these densities for all images, you will find that there's some bias towards the center, so people tend to look in the center. So in terms of Bayesian thinking, you would think of this as being the prior information, the prior distribution, which you would use to predict where people look if you don't know the image content. And this would be the posterior distribution after you have observed this particular image. This would be your best prediction where people look in this image. And so modeling saliency is about modeling basically this conditional probability distribution. Okay, so what we did then was the simplest thing that you can do. So we downloaded AlexNet from the internet, and we used it as is, as a filter bank. So you know these convolutional layers that are extracted in a deep convolution in your network. Basically, it consists of lots of images, again, that are somehow non-linearly filtered, right? And these images become smaller towards the top because people do downsampling in between. And so we had to reverse that, so we brought all these feature maps on the same size again of the original image size. And then all we learn are linear superposition weights of these feature maps to generate the two-dimensional saliency map in the end, the two-dimensional probability distributions where people look. Therefore, we have a softmax function here which normalizes our distribution, and we have one additional parameter which is a blurring kernel, which is a regularization parameter, and we include the prior saliency map as the n+1 feature map, because of course that's your a priori bet how your saliency map should look like. And then, all we had to learn were these linear weights. And here's the result. So this shows here lots of different models, and this is 100% is given here by a gold standard estimate, which actually uses the fixation of the people for the particular images. So it's not a prediction, but you still have to do a density estimate. So we use the kernel density estimate. That might be improvable. So it might be that this 100% is actually only 90% of the true information, but we are using it here as a gold standard. And with respect to the gold standard, basically the simple transfer learning trick boosted us from explaining 1/3 of this gold standard to more than 1/2. So from 34% to 56% of the explainable information. That's fun if you don't have to do much work. You just download something, do more or less something like linear regression, and you outperform 20 years of research by a large margin. And at that time, so you may recognize that this, we called this algorithm Deep Gaze 1. And the reason for that was that, of course, we knew ImageNet benchmark. People would continue to compete on the ImageNet benchmark, and actually at that time we already heard about the winners of the 2014 ImageNet benchmark, and we kind of liked the VGG19 network a lot, and so we thought, okay, the next thing that we will do is we download VGG19 and do the same thing again with that network. And then we will call it, we need a name for that, and we will call it Deep Gaze 2, and that will leave us room, if people get even better networks there, then we call it Deep Gaze 3, and when we end up with Deep Gaze 9, we have solved the problem completely. There's also other reasons to believe that this VGG19 network will show good transfer, or even would work even better on this benchmark. So this is adopted from Andrew Zisserman, who also did transfer learning on the Pascal 2 data set. And so AlexNet gave quite some improvement, but the VGG19 network got even much more improvement with the transfer learning paradigm on the Pascal data set. Okay, this is the typical visualization that I use for the VGG19 network, because that's so you have characterizes the structure, convolutions, pooling, and so on. So yeah, in comparison to AlexNet, it's even simpler. So it always has 3x3 convolutions and ReLU and max pooling and nothing else. So it's a very elegant, very clean scheme. So many of the specifics in the original network weren't necessary, and now, of course, we have much more experience with that. Okay. So again, we did the same trick. We just extracted the feature maps now from the VGG network. We striving for maximum performance. We allowed a little more, so we did 1x1 convolutions with ReLU on top, two layers, which you could think of allow us to learn a more interesting point-wise nonlinearity on top of these feature maps. But then, in addition, just the regularization parameter and the saliency map again. The center bias saliency map. And with that, we got to 86%, which basically tells us that within, I think, 1 year or so, just by transferring the knowledge from the ImageNet benchmark, we could make a big progress on this problem. give you also some visual impression how these different things look. Here's an image. Here's like the gold standard with the kernel density estimate. Here's the prediction of deep gaze 2. This was deep gaze 1, EDN and luminance contrast. So you can see it becomes more and more blurry. So it's by eye, it's not so easy to quantify. Here we have a matrix of pairwise Jensen-Chen divergences. So it's basically how easily you could discriminate the prediction of these saliency maps. And what you can see is that you have a clear cluster here between the gold standard, deep gaze 1 and deep gaze 2. So these three are in one cluster, and all the other models are in another cluster that can basically be perform similar to the luminance contrast prediction. This also holds true if you average over all the images. So this is the average Jensen-Chen divergence. And what I want to highlight a little more is what we have done recently is we try to get a better idea of the difference of these high-level models from these from a very simple local luminance contrast model. And so we improved the local luminance contrast model a little bit such that this one actually also outperforms these networks. So you could say that these previous networks weren't better than a model that was trained in a good deep learning way with very simple features that basically only use local luminance and local contrast. And what that means is basically you do something like a Gaussian pyramid, so you extract at different scales the average illumination and the average and the contrast energy in a local region. And since we don't know what local means, we do it at different scales and let the network figure out what the right scale is. So what we do is we use those feature maps, and then we only do one by one convolutional net layers afterwards and train them with a typical with the same machinery that we use with backpropagation. Right, and then we can ask, what are the images where the deep gaze network performs better? And these are like the images where you have the biggest advantage of using this deep gaze network above a local luminance contrast model. We can see that there are faces and written stuff here, and that becomes even more obvious from these examples. So what really is, pops out when you inspect the images is that deep gaze does much better than the other models in picking the faces and text and explaining that saliency. Okay, another story to this that I want to bring up is something when you work with benchmarks. So I really think benchmarks are important, and probably we wouldn't. Probably we wouldn't work with neural networks today if there wasn't a benchmark that have shown that neural networks perform better than other algorithms, because neural networks weren't very popular, right? So neural networks were they're messy, right? So it's hard to tell what they are actually doing. And unless you're sure that they're performing much better, there's no good reason to use a neural network. And in the past, it was always that much simpler algorithms performed better, or at least as good as a neural network, so there was no good reason to use a neural network in terms of performance. But now we have this big advantage, right? But in general, I mean, benchmarks can be quite tricky, and there are many possible pitfalls, and it's hard to, or one really has to think about various aspects. And so the reason why we worked at this saliency benchmark at that time was because one of my PhD students, Matthias, who actually also did the work with Bethge, then later, during a journal club, he got upset about the discrepancies of the different metrics on the saliency benchmark. So depending on which metric you use, the ordering of the models changes dramatically. And so we were wondering, okay, what's the right metric here? If you do model comparison, if you have a benchmark, at least after you did your test, you want to know which model is the best, right? And interestingly, this metric that I've shown you, that wasn't part of this, of these 8 different metrics that are provided at the benchmark, even though from our perspective, as with the Bayesian background, we think information gain is the right thing to do. You can actually interpret how many bits per fixation your model explains better than another model. And that's why we introduced that measure, and it also, just to give you an idea, because it actually applies to any kind of uncertain prediction problem. If you quantify information gain, you have experience with that. It's a very intuitive measure. So in this case, the intuition is imagine your a priori distribution is a uniform distribution within this area. Then if your model explains 1 bit, it corresponds to a shrinkage of your uncertainty, where people will look from this size to this area. And if you have 2 bits, it will shrink it to this size, and if you have 5 bits, it will become as localized as this. Right? So it's a clear measure of localization. And so I will try to make this point very quick, but this plot here shows all these 8 different other metrics as a function of the information gain explained. So this was our metric, these were the other metrics in a normalized fashion, which basically shows that that you have a non-monotonic relationship between the two. And the reason we figured, one of the biggest reasons why you have these differences is that the definition of saliency maps wasn't really tied to having a probability distribution. And so when you compensate for this lack of a precise definition, then you could make all these measures very consistent with each other, such that the correlation is between the different metrics was close to 0.9. And I mean, so we figured that this demonstration wasn't enough to, or it's still too complicated, too mathy. But what is simpler to explain is, imagine you have measured this saliency map here, or this probability distribution where people look for this image. And now you assume different metrics for this ground truth probability distribution. You would get different optimal saliency maps depending on which metric you choose. And that is a common thing in Bayesian decision theory, that if you have the posterior distribution, and now you, depending on which loss function you choose, say you have mean squared loss, then the best thing to do is to pick the mean of the posterior distribution. Or if you have the 0-1 loss, then the best thing is to take the maximum of the posterior distribution. So depending on what the loss function is for your task, you would make different decisions. And in the same way, these different metrics that are used in saliency benchmarks are related to different loss functions, such that even if you know the true distribution of fixations, you cannot have one saliency map that is optimal with respect to all metrics simultaneously. And this is actually quite a severe problem. So if you look at the predictions of that the different models give in terms of the probability density, then the discrepancies between these different models is relatively small in comparison to the discrepancies that you get in the optimal saliency maps. Okay, I talked a little too long about this part. But I've enough time to mention some other important ideas. And so far, I talked about benchmarking as one way to evaluate biological fitness. Another way, which I find very intriguing, is to test models with searching for adversarial examples. And so this is how we like to test models usually of our colleagues, right? So in scientific theories, if someone has a theory, what you do is you think, okay, what's the craziest prediction that this theory could make? And this is how you can break a theory, right? You find a counterexample to the most surprising prediction that a model would predict. And for deep neural networks, it's since everything is differentiable, so you can replace your colleague who is trying to break your theory by a gradient search for examples that are most likely to generate weird predictions. Yeah, let's put it that way. So what I'm referring to is the problem of adversarial examples. Imagine your network responds correctly to this image as being a dog image. And now you can do a gradient descent over the pixels of your image in order to reduce the dog activation and increase, say, the ostrich activation. And in this way, you can turn anything into an ostrich. And interestingly, for these networks, you need only tiny change, relatively small or tiny changes, but for us perceptually invisible changes in order to turn the classification into an ostrich. So the difference between the two for us is basically invisible. For the network, it changes the categorization. And there are two different ways. I mean, so some people react to this and think, oh no, these networks are all crap and it doesn't work at all. And other people think, okay, with deep neural networks, you can always generate adversarial examples. And even if we could backpropagate to our brains, then we could also come up with adversarial examples for our brains. And there's some truth to it, I guess. So it might be, since our brain cannot have a perfect model of the world, there will always be failures, and it might be possible that you can find also quite compelling failures. And visual illusions are sometimes also perceived as compelling failures. But I think it's really about how easy it is to find these and how sensitive your network is to these problems. And there I think there's still a big difference between human vision and machine vision. And so we are very interested in better understanding these problems. And one thing that we also, one way to demonstrate this type of, what the possible reasons for this failure is to use our style transfer algorithm. So here, just to remind you what you do when you do style transfer, you have two types of images, and basically you try to generate a new image by optimizing over the input such that you reproduce the texture information from this image and the content information from this image. And the texture information is, as you can see, that is basically doesn't preserve absolute position. It only maintains relative position of objects. And the content information doesn't preserve necessarily the actual appearance, but it has a notion of where things are, where objects are. So it's a bit like the power spectrum and the phase spectrum in the Fourier decomposition. So you can think of this as a cool higher level phase spectrum and this as a cool higher level power spectrum, which you then try to recombine. And here's how you can do this also for images, but you can also try to generate adversarial examples from this by taking two images from the ImageNet benchmark. So say this one, which is called the Model T class, so it's in car, obviously, and here from the Leopard class. And if you use the Leopard as style for this image, you generate something like this. And interestingly, I think my perception at least still rather sees a car here than a leopard, but the network is much more certain that this is a leopard than a car, which indicates that these networks are still very, very sensitive to texture rather than the actual arrangement of objects. And you can also demonstrate this by looking at the top 5 activations of the network for the regular image, the original image, and texturized versions of it. You'll find that the activations are very, very similar. So there's nothing built in, or it's not so clear how to deal with these spatial arrangements of things. And so here's another example. So this is interpreted as a lynx, but if you do color preserving style transfer, so we kind of extended this method recently to only transfer certain aspects of style, then in this case it is still, like our perception, interpreted as a boat. But if you use a different color preserving style method, so we introduced 2 in this paper, then it actually thinks it's a stingray, so you can get also very different things. But in general, I think it shows that the classification, so that it aligns with this earlier work, is a lot about texture classification. And currently we are, so this is work in progress. We are building, we are trying to simplify this network dramatically as a backup feature type of network. And we are currently at 76% performance. So it's the VGG network has 86% on ImageNet. And so as soon as we have 86%, we have a very simple explanation of how you can achieve VGG net performance with less layers and in a much more understandable way. I guess I have 2 more minutes, 1 more. I will wrap up now. I just want to try to summarize. So this was scratching at the issue that there's a transition between objects and stuff. So if you have many objects and there are different locations, things tend to become stuff. And this is also what you do when you pool in these networks, that you sort of become more insensitive. But our visual system also allows you to focus on one of these objects, to pick them out and to think about their spatial arrangement again. And this is something that is not so easy to do with the same precision as we can do in Confluence. And for us, it's also the visual system is always high resolution in the fovea and less resolution in the periphery. So there seems to be a mid-texture-like representation in the periphery and more an object-segmented representation in the fovea. And maybe, so as a final content here, so there are many, many ideas that I think are important to play a role for this problem of adversarial examples. So the adversarial examples, I think, reveal an important discrepancy between human vision and machine vision, and they have to do, for instance, as I just alluded to, with the lack of an explicit representation of spatial arrangement. Of course, there are tasks like semantic image segmentation, which are very important, and there's the ADE20K dataset, which I'm quite excited about, which allows you to do classification with lots of classes with segmentation. But there are also other ideas like generative modeling, that analysis by synthesis can help to resolve this problem, better regularization, better inductive biases, that, for instance, we have shift invariance built in, but we don't have scale invariance built in, and other problems. And for instance, uncertainty estimates are in general not very good in these estimates. So the probabilities that the networks throw out are not well trained yet. And I think in all these points, there's promising work coming out, but we need to bring this together in order to match human performance. And so now I wasn't sure how fast this will go, so I have a lot of slides. Yeah, maybe. So I'm dreaming of building a vision-like architecture, similar a little bit to those who know to this DeepMind attention network, where you actually collect visual information in a sequential fashion, where a peripheral network guides your fovea into regions that are informative. Just that this shouldn't only work for house numbers, but actually for real images, and maybe for car driving or for searching your key in a messy room, maybe. And so I want to thank my group here. So in my group, we have people working on theory of deep neural networks. We have people working on neuroscience and perception. So I like really bringing these different aspects together. And we recently also started a collaborative research center. So we have now more than 20 labs really trying to, from both neuroscience and machine learning, trying to understand the robustness of vision. And thank you for your attention. I probably used up my time a lot now.
Yes. Thank you. Are there any questions? Yes?
In the beginning you were talking about gaze estimation, later on to style transfer. Would it be possible to take an image and then use this style transfer to kind of guide the gaze of a person into a certain spot of that image? So you're painting these images to look like ostriches, for example, but can you do the same for making a certain spot appear more interesting to the human eye?
Actually, we are working on that. But yeah, it works already. Yeah, but there are also you also fight with adversarial example problems. So if you simply search for like maximizing the saliency in certain regions with the deep gaze network, then it can happen that you run into adversarial problems. But with using these textures is a good idea because that is less prone to adversarial problems.
Another question, maybe? Yes.
I never really understood how bad these adversarial examples are in actual application. So are they indicating a real problem? Can you find these examples without actually using the parameters of the network to search for them specifically?
Yeah, so I showed you, I mean, the way how I generated adversarial examples was not using a search, so it was just merging the textures. There are also other works which show that you can search for adversarial examples with one network and they generalize to other networks. And the question how harmful they are is, I think, that related also to so as long as you stay sufficiently in what machine learners call the IID domain, so if your new images on which you test are sufficiently identically distributed as the ensemble on which you've trained, it won't be a problem, because then you wouldn't go into these areas where you test when you do adversarial examples. And that would be a little bit like if you explain the movements of the planets by IID predictions, right? Then you might not extract Newton's law, but you just have a predictive description of these movements, and that would work. But now if you want to make predictions about something under completely different circumstances outside that ensemble, then it wouldn't generalize. And I think the actual cool challenge is to find ways to extract the causal factors, causal latent variables underlying vision. And for those, you would also hope that adversarial or that your system is much more robust against adversarial testing.
Okay, last question.
About your saliency prior. Would you say that you are overfitting in that way? Because I would claim that it's not really, it's not the preference of the viewer, but it's actually the bias of the one taking the picture, that the object or saliency is in the center.
It's the, I mean, the center bias comes out as a result, as an average just over all images where people look. So it's, in that sense, it's not even a prediction, therefore not overfitting, but it's just a description of what people do. Now maybe you can rephrase or say your question again.
It's a description of the content, but I would say the bias comes from the one taking the picture rather than the one using.
Ah, okay, yeah. So, I mean, there are many, that's true. So there are also data sets. So my colleague Felix Wichmann, he also didn't like the center bias, and so he asked his student to go into the forest and make as random pictures as possible. And so there you have much less center bias, but it's also related to when you sit in front of a screen. It's an economic decision to look at the center, and this is related to the general finding that the patterns where people look depends a lot also on the tasks. So we also did some investigations into task dependencies, into temporal dependencies, and so on. But for now, I mean, this simple setting is basically ideal to get your methods straight and to get your optimization going before you want to dive into all the complexities of the system. But there are many exciting questions regarding the temporal dynamics, regarding task dependencies, and so on. We are hoping to address at some point.
Let's thank the speaker again. And see you next time.